In this lesson, 10.2, Taylor Polynomials and Approximations, we will find a process to write a polynomial function that will approximate functions such as sine x, cosine x, e to the x, and ln x. These approximations are known as Taylor polynomials. In fact, the tangent line approximation, f of x is equal to f of a plus f prime of a times x minus a is a Taylor polynomial of degree 1 that approximates f of x for x near a. If a equals 0, this special case is called a Maclaurin polynomial. So basically, you have a function. Let's say, for instance, we have a function, I don't know, like sine of x or something. So here's our sine of x. Let's say we would like to center an approximation at pi over 2. So we would start with this point, and we would first find a linear function. And our linear function might be like that, right? Because I know that it's at its highest point at pi over 2. So therefore, that's going to be the equation of your tangent line. If I chose something like pi, my equation of my tangent line is going to be like that, right? But that's the first of your Taylor polynomial. These are both Taylor polynomials because they're centered at x equals pi over 2 or x equals pi. If I would center it at x equals 0, okay, let's say I centered it at x equals 0, and I would have this is my first Taylor polynomial because it's the equation of the tangent line. It would be considered a Maclaurin polynomial because it's centered at x equals 0. So if as you go higher, like let's say a quadratic or a cubic or a quartic or, whatever, fifth degree, sixth degree, seventh degree, the longer you go, a lot of times, the better the approximation is, okay? So for sine and cosine, that is absolutely true. If we took it to the nth degree, it would be exactly equal. Even though it would be a polynomial, it would be exactly equal to either cosine or sine. Some of the polynomials, the Taylor polynomials and the Maclaurin polynomials, are only good for one point, like at one x value, or some of them are good for an interval of x values, okay? And again, I think I showed you that with the last video that I did. So we constructed Taylor polynomials from scratch on the last video. The following formula will be extremely important for the rest of this unit, and you must know it by heart. Definition of an nth degree Taylor polynomial. If f has n derivatives and x equals c, then the polynomial p sub n of x is equal to f of c plus f prime of c times x minus c plus f double prime of c divided by 2 factorial times x minus c to the second power plus dot 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 f to the nth derivative of c over n factorial times x minus c to the nth. That is called the nth degree Taylor polynomial for f at c, named after the Brooke Taylor, an English mathematician. If c equals 0, then p sub n of x equals f of 0 plus f prime of 0 times x plus f double prime of 0 times, or divided by 2 factorial times x squared plus f triple prime at 0 divided by 3 factorial times x cubed plus dot 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 f to the nth degree derivative at 0 divided by n factorial times x to the n is called the nth degree Maclaurin polynomial for f, named after Colin Maclaurin, a Scottish mathematician. So the only thing that changed is right here the x minus 0, because my c is 0, just becomes x. So that's the only thing that changes. I want you to notice that the number of the derivative, you're always dividing by that number's factorial, and you're taking x minus c to that power. Okay, so if this is the first derivative, it's divided by 1 factorial and taking x minus c to the 1 power. Now, you could even think of this one as f of c being the 0 derivative, which means there's no derivative at all, and then dividing by 0 factorial, and then taking it to the x minus c to the 0 power. And so if you thought of it that way, then every single one of those terms gives you, it's like your derivative divided by the derivative, the number of the derivative factorial times x minus c to that number power, because this whole thing would just become f of c, which is what they have there. Okay, so example number 1. Suppose that f is a function which has continuous derivatives, and that f of 2 is 1, f prime of 2 is negative 3, f double prime of 2 is 5, and f triple prime of 2 is negative 7. Write the Taylor polynomial of degree 3 for f centered at c equals 2. So this is going to be p sub 3 of x, because really that's going to be n equals 3, right? Because it's the degree 3. And so the first thing you're going to look at is your f of 2. And that is 1. And then plus, you've got your f prime of 2, negative 3 divided by 0 factorial, divided by 1 factorial times x minus c, which would be x minus 2. And then plus, we've got f double prime at 2. And that is 5 times x minus 2 to the 2nd power divided by 2 factorial. And then plus, we've got f triple prime of 2 is negative 7. So we have negative 7 times x minus 2 to the 3rd power divided by 3 factorial. So that would be your Taylor polynomial of degree 3 for f centered at c equals 2. Example number 2, use the formula above to construct a Taylor polynomial that approximates f of x equals sine x, centered at x equals 0, of degree 5, a Maclaurin polynomial, because it is centered at x equals 0. So what we're going to do is look at our function and our function at 0. Then we look at the first derivative of our function and the first derivative at 0. Then the second derivative of our function and the second derivative at 0. And then the third derivative of our function and the third derivative at 0. The fourth derivative of our function and our fourth derivative at 0. The fifth derivative of our function and our fifth derivative at 0, because they want a degree 5. So now we're going to use that to create our Taylor polynomial. So that would be p sub 5 of x is equal to, the first one is f of 0, which is 0. Okay, so I'm not even going to write it. Then f prime of 0 times x minus 0, so that's just going to be x, divided by 1 factorial, which is just 1, so that's just going to be x. The second derivative is 0. The third derivative is negative 1 times x to the third divided by 3 factorial. And then the fourth derivative, 0. Fifth derivative, positive 1 times x to the fifth divided by 5 factorial. If we kept going, oops, oh my. Sorry about that. Our Taylor polynomial, which since it is at x equals 0, it is more specifically a Maclaurin polynomial, would be p sub n of x is equal to x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus dot, dot, dot. And of course it's going to go plus, minus, plus, minus, plus, minus the whole time. And that last one, to get it to change from positive to negative, we're going to put negative 1 to the n. And to make sure that we have an odd number here as a power, we're going to say 2n plus 1. And we're going to divide that by, we want odd numbers for factorial. So we're going to put 2n plus 1 factorial. And this would give you a Taylor polynomial or a Maclaurin polynomial that would be exactly the same as the sine of x. And we're going to look at that on the calculator in just a minute. So example number 3. Write an nth degree Maclaurin polynomial for f of x equals cosine x. So you can see how we go about doing this. We start with f of x equals cosine x, and then we start with f of 0. Then we take f prime of x, and that is negative sine x, and we find f prime at 0. Then we take f double prime of x, which is going to be negative cosine x, and then we find f double prime at 0, which is negative 1. Then we take f triple prime of x, which is positive sine x, and we take f triple prime at 0. And I think I went all the way to the fifth, just because we've got 0. Oops, we did x first. We get 0 on every other one, so you have to take it kind of, you have to take it kind of far out to see the pattern. So fourth derivative was cosine, and the fourth derivative at 0 was 1. Fifth derivative is negative sine, and the fifth derivative at 0 is 0. And we could keep going because we're doing it to the nth degree. So this is going to be p sub n of x is equal to, and we look at the first one, we get 1. And then we have, the next one is 0. The next one is minus 1, and this is our second. So this is going to be x to the second divided by 2 factorial. This one was 0 factorial. 1 factorial went away. This is 2 factorial. And then 3 goes away. 4 is a positive 1. So this is going to be positive 1 times x to the fourth over 4 factorial. Fifth goes away. If you want to think about it, you could think, oh, well, that must be negative. I put positive, sorry. Sometimes I put plus or minus, but I'm going to go ahead and put minus x to the 6th over 6 factorial plus dot, dot, dot. And now you can think about, okay, it's changing signs every single time. And this is even powers, so 2x to the 2n. 2n will always give you evens. And then even powers on the factorials. And of course, if we write it like this, you're probably wondering, how would I get positive 1 as my first term? This is assuming that this is summation n equals 0 to infinity. If you wanted it to be summation n equals 1 to infinity, you would have to change the n's in the exponents, okay? So, and I think that was the same up here, and I just did not point it out, that first thing I forgot to point out was that if you need odd numbers, if you notice that the pattern is producing odd numbers, you need to either use 2n plus 1 or 2n minus 1, depending on which one's going to give you what you're looking for. And I also wanted to say that this is only going to be true if the summation was n equals 0 to infinity. So, you know, if you wanted n equals 1 to infinity, you'd have to adjust it. And the same thing goes true here, 0 to infinity. And we need to remember that 2n is going to give us even numbers. Okay, so 2n produces even numbers. And that's why we use 2n there. All right, example number 4. Write an nth degree Maclaurin polynomial for f of x equals e to the x. So we start out with f of x. And we take f of 0, because it's a Maclaurin, so it's at 0. E to the 0 is 1. And then we take the derivative, e to the x. And the derivative at 0 here is 1. Then we take the second derivative, e to the x. The second derivative at 0 is 1. We take the third derivative, e to the x, and the third derivative at 0 is 1. So you can see that you are producing 1 every single time because you're producing e to the x every single time. So if I wanted my Taylor polynomial, or more specifically my Maclaurin polynomial, because I'm centering it at x equals 0, I have f of 0. I have plus f prime of 0 divided by 0 factorial, divided by 1 factorial times x to the 1. Plus, and then this is 1 divided by 2 factorial times x to the 2. And this is 1 divided by 3 factorial times x to the 3. And you can see how that keeps going. And so if I wanted to write the nth term, it's going to be x to the n over n factorial, and that's if the summation n equals 0 to infinity is used. Okay? But this right here is the nth term. This right here is the nth term of your Taylor polynomial. So you will be required to memorize the Maclaurin polynomials for the 3 functions we created. It is important to recognize them in general form, sigma notation. So for this one, you're going to say summation n equals 0 to infinity. We've got our negative 1 to the n times our x to the 2n plus 1 divided by 2n plus 1 factorial. And we just need to remember that sine x alternates on odd numbers. And so we're looking at 2n plus 1 to produce those odd numbers. Cosine x summation n equals 0 to infinity, negative 1 to the n times x to the 2n divided by 2n factorial. And cosine of x alternates on even numbers. And so for those even numbers, to get those, we have 2n. Summation, so now e to the x, summation n equals 0 to infinity. And if you remember, we found out that that nth term was x to the n over n factorial. And e to the x increases on counting numbers. And the power equals the factorial. Okay. So now, technology tip. You can access the Taylor command on the TI-89 under the F3 menu or on the TI-Nspire menu 4C1. The syntax for either calculator is as follows. Taylor, open parenthesis, expression, variable, order or degree, and center. Both utilities will default to a center of 0 if you don't type a center. This is a good tool for checking your work, but all work is required to be written on the AP exam. So example number 5, use the Maclaurin Polynomial for f of x equals sine x from example 2 to find the Taylor polynomial of degree 5 at 1.5. So what I did was go back to example number 2 to remind myself what the fifth degree Taylor polynomial was, and it was x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. So that is what sine of x is as a Taylor polynomial. And so now, if you put this into your calculator and then find the p sub 5 of 1.5, and of course you don't have to call it p sub 5 in your calculator, it's a y equals. But if you find that value at 1.5, you should get 1.000782125. And if you want to, we can go to Desmos. And the Desmos calculator, if I wanted to put in x minus x to the 3rd divided by 3 factorial and I don't see my factorial button. Need to be down there. Okay. I don't see the factorial button on this. I did it on my CAS to get the answer. So I was thinking I could do it. I could show you how to do it on Desmos, but I did not practice that. So anyway, that's your answer. What is the value of f of 1.5? Well, in example number 2, we were approximating the sine of x. So basically what they're asking here is what is the sine of 1.5? And if we put sine of 1.5 in our calculator, we get 0.9974. Sorry, 9974 949 86604. I know I'm taking it several places out on the decimal point, but you can, decide what the problem asks you. Sometimes mathematicians want you to take it that far out, so I don't think it hurts to practice it. And then what is your error in your approximation? So you're going to take your exact, the absolute value of your exact minus your Taylor polynomial at 1.5. And so if you do that, you should get 0.00328626396. And then part B, find P sub 5 of 2. So if we were finding P sub 5 of 2, I would do that in my calculator, because you would be finding, or not P sub 5, it's not summation, I'm sorry. That's going to be your P sub 5 of 2. And you're going to put that in 2 minus 2 cubed over 3 factorial plus 2 to the 5th over 5 factorial. And you should get here 14/15, 0.9333, and it keeps going. What is the value of f of 2? So for f of 2, you are using your sine function. So sine of 2, you get 0.909297, 426826. And then if f of 2 minus p sub 5 of 2 is taken absolute value, what does it equal? And so when I did that in my calculator, I got 0.0240359 06508. How does the error for p sub 5 of 2 compare to the error for p sub 5 of 1.5? So p sub 5 of 2 error is greater than the p sub 5 of 1.5. What would happen if we use the polynomial to estimate the sine of 2.5? The farther away you are from the center, the greater the error will become. Okay, so remainder, error, and accuracy of a Taylor polynomial. When we use Taylor polynomial approximations, it would be good if we knew how accurate they are to the exact values of the infinite series. The function value estimated by the Taylor polynomial can be defined by the concept of a remainder, such as f of x equals the nth Taylor polynomial at x plus r sub n times x. So exact value equals the approximate value plus the remainder. So the absolute value of the remainder, r sub n of x, is called the error. The error is the absolute value of r sub n of x, which is equal to the absolute value of f of x minus the Taylor polynomial, the nth Taylor polynomial at x. In order to use Taylor polynomials effectively, we will use Taylor's theorem to estimate the size of the error. The remainder given in the theorem is called the Lagrange form of the remainder, or the Lagrange error bound. This gives us a bound for the error, not the exact value of the error. Okay, so you got to remember that, not the exact value of the error. It gives you a range for the error bound. For now, let's think about the error as follows. The error is the absolute value of the actual minus the approximation. Again, another good thing to remember. So now, Taylor's theorem. If a function f is differentiable through order n plus 1 in an interval containing c, then for each x in the interval there exists a number z between x and c, such that f of x equals f of c plus f prime of c times x minus c plus f double prime of c divided by 2 factorial times x minus c squared, dot, 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 dot. And then look, this is the nth term, and this is the remainder. So the remainder is the n plus first term. Notice that this is the n plus first derivative divided by n plus 1 factorial and multiplied by x minus c to the n plus 1. So Taylor's inequality, or the Lagrange form of the remainder, is absolute value of r sub n of x is less than or equal to the absolute value of m divided by n plus 1 times x minus c to the n plus 1, where c is the center. M for maximum is defined to be the maximum value of f of n plus 1 of z, where z is between x and c. Bounds on the remainder found using this form are also called Lagrange error bounds. We will explore errors and accuracy with Taylor's theorem in the last lesson of this unit, although I must admit I don't think it's on the AP exam. So example number 6, given the second degree Taylor polynomial is a plus bx plus cx squared, is the second degree Taylor polynomial for f about x equals 0. What are the signs of a, b, and c if f has the graph pictured on the right, and explain your reasoning? So what I want to think about is, this is my original function. And if I think about it and think of this as f, right? So that's our f of x. And look at what's happening at f of 0. F of 0, it's down here in the negative. So it's below the x-axis. So I know that f of 0 is less than 0. And why? Because that is my y-intercept. And I just wanted to notice that my y-intercept is negative. That means my y-intercept lies below the x-axis. So why does that matter? Well, that's our a, right? That is our a. That's our f of 0. So now we know, therefore, a is less than 0. And then we want to think about the the first derivative at 0. So f prime of 0. So if I imagined what the derivative, the slope of the tangent line would be, it would be negative. Do you see how that is decreasing? So I know that my f prime of 0 is less than 0. And that means that my f function is decreasing, right? Because if I did if my derivative is 0, I know it's going to be negative, meaning it's decreasing at x equals 0. That's the reasoning. And this is going to be my b. So I know that my b is less than 0. Because remember, I'm using this right here, guys. That's where I'm getting my a, b, and c, right? So now on for the last one, what about my second derivative? So my f double prime at 0. Well, look, this is concave up. Do you see how your function right here is concave up? So that's telling me that my second derivative is positive. So my second derivative is greater than 0. And I'm going to say f is concave up at x equals 0. That's my reasoning. So therefore, my c is greater than 0. And so that's what they were asking. And I explained my reasoning. I know that my a is less than 0, my b is less than 0, and my c is greater than 0. So let's go to example number 7. Suppose that the function f of x is approximated near x equals 3 by a third degree Taylor polynomial. T sub 3 of x equals 4 minus 5 times x minus 3 to the second power plus 6 times x minus 3 to the third. Find the values of f of 3, f prime of 3, f double prime of 3, and f triple prime of 3. So I would like to just think about this Taylor polynomial of degree 3 and think about that. We know that we've got our b times x minus 3 squared over 2 factorial, and we've got our plus c times x minus 3 cubed over 3 factorial. Think about that's, and that this would be your f of 3. Okay? And what's missing? Your f prime of 3 is missing, because we don't have anything times x minus 3 to the first power, and that's your first derivative. That involves your first derivative. This is all about your second derivative at 3. This one is all about your third derivative at 3. So now we can see that these are going to be our answers, that f of 3 is 4. So that's one of our answers. And f prime of 3 is 0, because that zeroed out that one with the first derivative, because there wasn't anything there. Okay, and I put because there is no x minus 3 to the first power term. Okay, that's the reasoning. If I want to find my f double prime of 3, I'm going to have to say that my b over 2 factorial is equivalent to negative 5. So I know that 2 factorial is just 2. So I'm going to multiply by 2, and I can see that my b is negative 10. And so that's going to be my f double prime of 3, negative 10. And my reasoning is right here, this algebra. And then for f triple prime of 3, I'm going to take c divided by 3 factorial and set that equal to 6. Remind myself that 3 factorial is 3 times 2 times 1, which is 6. Multiply by 6 on both sides, and I get c is equal to 36. And from that one, I can see that my f triple prime at 3 is 36. So what ended up happening there when they went to create that Taylor polynomial, when they put negative 10 in divided by 2 factorial, it became negative 5. And when they put 36 in divided by 3 factorial, it became positive 6. So all we were seeing here are those values, you know, after they simplified the fraction. So to find the a, b, or the, f of 3, f prime of 3, f double prime, and f triple prime of 3, we had to figure out what that original value was. Part B, does f have a local maximum, a local minimum, or neither at x equals 3? So let's think about that. We've got x equals 3 here, and we know that the derivative at 3 is 0, and we know that the second derivative is negative 10. So it's negative. So that means we had concave down here. And if we have concave down, that means we have a maximum at 3. This is the second derivative test. Okay, so all we could do is use the second derivative test, because typically we say, like, okay, what is f prime? But we didn't know what f prime of 2 was. We didn't know what f prime of 4 was. But we did know the second derivative at 3. And if the second derivative at 3 is less than 0, that's concave down, and that means you must have had a maximum. So to explain that, we're going to say f prime of 3 equals 0, and f double prime at 3 is less than 0. So by the second derivative test, f has a local maximum at x equals 3. Okay, oops, and I think we are done